Hi, hi guys. My name is Samuel Jasper from CSE department. My topic for probability and statistics for Tech Talk is on joint mass and density functions. Before deep diving into what is joint mass and density function, let us know what is joint mass and density functions. Introduction. What are joint distributions? A joint distribution describes the probability behavior of two or more random variables simultaneously. It generalizes the concept of a single variable distribution, marginal distribution, which is also known, to multiple variables. It is essential for studying interactions, dependence, and correlations between random variables. These are known as joint distribution. Joint mass and density functions extend the idea of a probability distribution from a single random variable to multiple variables simultaneously. They are essential for understanding interactions, dependence, and correlations between variables in both discrete and continuous settings. By studying joint distributions, we can model complex real-world phenomena, compute probabilities for multiple events, and derive meaningful statistical measures such as covariance and correlation, which are crucial for decision making and prediction in various fields. Studying joint mass and density functions is motivated by the needs to analyze multiple random variables together. Marginal distributions alone fail to capture the dependencies and interactions between variables, which are critical in fields like finance, engineering, and metrology. Joint distributions allow the calculation of combined probabilities, conditional distributions, and measures of dependence, providing a comprehensive framework for multivariate analysis and decision making. Let's deep dive into joint mass function. Let's see what is mass function is all about. In math, joint mass function is a discrete random variables x and y. The joint probability mass function PMF is P x f x of x and y is equal to P of x is capital X is equal to small x and capital Y is equal to small y. It gives the probability of every possible pair of outcomes. The properties of joint mass function are probability of x and y uh, is in between 0 to 1 for all x and y values. The sum of all probabilities in joint mass function is equal to 1 or below 1 and greater than 0. The formula for joint mass function is summation of x, summation of y, probability of x and y is equal to 1. It Let's see what are the independence factors. X and y are independent if probability of x and y is equal to probability of x multiplied with probability of y, where x and y are integers. Independence means knowing capital X gives no information about y and vice versa. The joint probability mass function provides a complete description of the probabilities of all possible pairs of discrete random variables. It allows calculations of marginal distributions, tests for independence, and helps in computing probabilities of combined events. Understanding joint PMFS is foundational for discrete multivariate probability analysis, and it is widely used in games of chance, reliability studies, and decision-making problems. Earlier, we have said what is joint mass function. Now, let's see what is joint density function. The definition for joint density function in maths is continuous random variables where x and y are the random variables. The joint probability density function PDF is function of x and y such that probability of x is in between a and b, and y is in the between c to d, is equal to integration of a to b double integration of c to d a function of x and y dy dx. Unlike discrete probabilities, function xy itself is not a probability. Probabilities are obtained by integration over a region. The properties for joint density function are: it is non-negative. It means a function of x and y is always greater than 0, and total probability is equal to 1. The formula for joint density function is from double integration of minus infinity to infinity and minus infinity to infinity f of xy dy by dy multiplied dx is equal to 1. The joint probability density function extends the concept of joint probabilities to continuous random variables. By integrating the joint PDF over a region, we can compute the probability that the variables fall within that region. Marginal distributions and independence can also be derived from the joint PDF. Joint density functions are essential for modeling continuous multivariate phenomena such as heights and weights, finan- financial returns, or environmental variables. Condition distribution. Let's see what this condition distributions is all about. For discrete random variables x and y, probabilities of capital X is equal to y and capital Y is equal to y is equal to probability of x. Capital X is equal to x and capital Y is equal to y divided by probability of capital Y is equal to y. Probability of capital Y is equal to y is always greater than 0 and is not less than 0. The properties for conditional distributions are: conditional PMF satisfy a summation of x probability of capital X is equal to x and capital Y is equal to y is equal to 1 for each fixed y. Conditional PMFs are themselves valid probability distribution. For example, rolling two dice, x is equal to capital X is equal to outcome of dice 1 and capital Y is equal to outcome of die 2 gives given y is equal to 5 conditional probability that x is equal to 3. Here we can see the formula applied to the above statement. Probability of capital X is equal to 3 and capital Y is equal to 5 is equal to probability of capital X is equal to 3, y is equal to 5, and it is divided by probability of y is equal to 5. Continuous case. It for different continuous random variables x and y, function of x and y is equal to function of capital X y divided by the function of y. Conditional distributions provide the probability distribution of one variable given that another variable takes a specific value. In the discrete case, conditional PMFs are obtained by dividing the joint probability by the marginal probability. In the continuous case, conditional densities are obtained by dividing the joint density by marginal density. Conditional distributions are essential for understanding dependence between variables, performing regression analysis, making predictions, and applying Bayesian methods. They form a crucial link between joint distribution and practical statistical inference. Expected value, covariance, and correlation. Definition for discrete case. Capital E of x is equal to summation of x summation of y x multiplied with probability of x and y. The definition for continuous case is E of x is equal to double integration of minus infinity to plus infinity x multiplied with function of x and y dy dx. Interpretation: average or mean value of x considering the joint distribution with y. For example, rolling two dice x and y, E of x gives us summation of x is equal to 1 to 6 and summation of y is equal to 1 to 6. X multiplied with 1 by 36 gives us 3.5. Covariance. Definition. Covariance of x and y is equal to E of xy minus E of x, E of y. Interpretation. It measures linear relationship between x and y. Covariance of x and y when greater than 0, it means variables tend to increase together. When it is less than 0, it means one increases as the other decreases. When the covariance of x and y is equal to 0, then there is no linear relationship between x and y. For example, let's use dice example. X and y are independent, so covariance of x and y is equal to 0. Correlation. Definition. Uh, Correlation of x and y is equal to covariance of x and y by sigma x and sigma y. Interpretation. Standardized covariance stands in between -1 to 1. 1 is known for perfect positive correlation, uh, whereas -1 is known for perfect negative correlation. When a 0 comes into place, then there is no linear correlation. Expected value, covariance, and correlation provides measures of central tendency with linear and linear dependence in multivariate distribution. Expected value captures the average behavior of a variable within its joint distribution, while covariance quantifies how two variables vary together. Correlation standardize covariance to a dimensionless measures ranging from -1 to 1, indicating the strength and direction of linear relationships. These metrics are fundamental in statistics, finance, engineering, and machine learning for understanding dependencies and making informed decisions. Application. It is used in real-world examples such as biostatistics, meteorology, finance, engineering. In biostatics, heights and weights of individual; in finance, returns of multiple stocks; meteorology, where daily temperature and humidity is predicted. Statistical modeling. Joint distributions are foundational for multivariate probability models, machine learning algorithms, and simulations. Decision making. Condition probabilities guide predictions and decisions. For example, given high humidity, what is the probability of rain? Joint mass and density functions have wide range applications in science, engineering, finance, and statistics. They allow us to model, analyze, and predict outcomes involving multiple random variables by capturing joint behavior, conditional distributions, and measures like covariance, correlation, and they support decision making, risk assessment, and research in areas from biostatics to meteorology to finance and to machine learning. Joint distributions describe the behavior of two or more random variables. Continuous case joint PDF allows computation of probabilities over region. Dependence measure. Covariance and correlation quantify relations between variables. Conclusion. Joint mass and density functions form the backbone of multivariate probability analysis. They provide a framework for understanding the combined behavior of discrete and continuous variables, enable computation of marginal and conditional probabilities. These concepts are critical for practical applications in science, finance, statistics, and machine learning, allowing us to model complex systems, make predictions, and make informed decisions. Thank you.